Hi, welcome to MA 207 course. In this video, we are going to discuss about wave equation. We know that wave equation is double derivative with respect to x is equal to k square into double derivative with respect to x. Okay, first type of boundary conditions we have it is x is equal to 0 and l is equal to 0. Okay, and for this equation to solve, we need four boundary conditions. Boundary conditions are given here. Okay. U at t is equal to 0, we get f of x. With derivative of u with respect to t at t is equal to 0, we get g of x. Okay, we get the solution like this. We have alpha n into cos term plus beta into a scalar into here sine term. The whole with the product with sine term. Okay. We can find alpha and beta and by using this formula, that is Fourier series of f of x and g of x. Okay. For Newman boundary conditions, here only difference between the boundary conditions is here x is equal to 0 and l. The u derivative with respect to x is 0, and same here with f of x and g of x. We get the solution for the equation like this. The difference is here we get extra two terms, b naught of t plus alpha naught, and one more change is here we get cos term instead of sine term. We can find alpha naught and beta naught by using this formula, and we can find alpha and beta n by using this formula, Fourier series for f of x and g of x. To find the solution for non-homogeneous wave equation, we can use similar procedure. We have f1 of t and f2 of t in place of 0 and 0. So we can use zx comma t is equal to ux comma t minus 1 minus x by l f1 minus x by l f2. Then it transforms to this condition. Then we can find the solution of this by similar procedure as the heat equation. Let's see an example to get clarified. Here we have similarly we have 0 and 0 for initial boundary conditions, and we have x into x minus 1 in place of f of x, and g of x is 0, and here capital G of x comma t is e power t. So let's first find Fourier series for this and this. We're gonna use in the further steps. Okay, we found the Fourier series for this. Next, we are looking for a solution of the type like this. Okay, we substitute this equation in here in this equation. Then we get this expression. Here we equate this with this, the coefficient of sine n pi x. Then we get un of t is cn cos term and dn sine term. Let's take even n. Then we get the un of t is 0. Okay. Next, for odd, we get this expression. Okay. Next, we're gonna put un of t is c e power t. Then we get this equation. We get a solution. This as a solution. The general solution for this is given as un of t is this solution plus we got earlier cn cos n pi t plus dn sin n pi t. We can find the constant cn and dn by using the initial condition. If we equate Fourier series coefficient of x into x minus 1, we get cn, and similarly we can find the dn. So this is the procedure to solve the non-homogeneous wave equation. Similarly, for Newman boundary conditions, we can find z. We can transform this type of boundary conditions to this by applying z as given below, and we can find similarly the non-homogeneous wave equation for Newman boundary conditions.